Hello my dear students, welcome to the third lecture of geometrical optics. Till the last class we completed with plane mirrors, right? So in today's class we'll do some problems related to plane mirrors and then we will start with spherical mirrors. Okay, so let's start with the class. So first we'll do one question where we are given two blocks each of mass m. So we have two blocks each of mass m which lie on a smooth table. They are attached to two other masses as shown in the figure. The pulleys and the strings are light. An object O is kept at rest on the table at this point. The sides AB and CD of the two blocks are made reflecting. So this side and this side both are reflecting surface. Then what is the acceleration of the two images formed in those two reflecting surfaces with respect to each other? Alright. So first what I will do is I will draw the left pulley and I will apply Newton's laws of motion and find the acceleration of these two blocks. Okay. Suppose this is moving downwards with an acceleration A, then this will move left with an acceleration A. Okay. So you know that the acceleration will be, so here if I draw the FBD of this block, or one thing what we can do here is we can take these two together as the system. So the net force on this two block system will be 3 mg, right? And this will be equal to 4m into A, right? You can imagine that this, you have opened this string and on this side there is no force of gravity, but on this side there is force of gravity 3 mg. So you can draw it like this. Imagine that you have opened it. Okay, so when you have opened it, the 3 mg force is towards left and here there is no force of gravity in this direction because this is horizontal. Okay, so the net force on the two particle system will be 3 mg and that will be equal to total mass, that is 3m plus m, 4m into A. Tension becomes an internal force when you take the two particle system. Okay, so from here you will get A is equal to 3 by 4g. So this is the acceleration of the mirror A. Similarly, now if I will draw the right pulley, if I draw the right pulley, what I will do here, this is M, this is 2M, right? So here again I will open it and 2 mg force is towards right from this side and this side it is horizontal, so there is no force of gravity. So the net force on this two particle system is 2 mg and this has to be equal to 3m into A, right? Because net mass is 2m plus m, that is 3m. Net force is equal to net mass into acceleration. This is Newton's second law. Okay, so from here you will get the acceleration as 2g by 3. So the acceleration of C, this is 2g by 3 and this is 3g by 4 left and this one is right. All right, so now what I will do is, we know that velocity of image plus velocity of object is 2 times velocity of mirror. When you differentiate this, you will get acceleration of image plus acceleration of object is 2 times acceleration of mirror. Now in this case the object is at rest, so the acceleration of the object is 0. So the acceleration of the image is 2 times the acceleration of the mirror. So that means the acceleration of image 1 will be 2 times the acceleration of mirror. So A, mirror A is moving towards left with 3g by 4, right? So I'll write it as minus 3g by 4. So this is equal to minus 6g by 4, or you can say minus 3g by 2. This is the acceleration of image 1. Similarly, the acceleration of image 2 will be 2 times acceleration of mirror 2. Okay, and the acceleration of mirror 2 is 2g by 3 towards right. So I'll write the acceleration of image 2 is 2 into 2g by 3 and that is equal to 4g by 3. Now what they have asked you here is the acceleration of image 1 with respect to image 2. The acceleration of image 1 with respect to image 2 is acceleration of image 1 minus acceleration of image 2 and that will be equal to minus 3g by 2 minus 4g by 3. and this will come out to be minus 17 g by 6. Okay, minus only represent the sign or the direction, the magnitude of acceleration of one image with respect to the other image is 17 g by 6. So the answer will be 17 g by 6. Now let us look at the next question. In this question, it is given that two plane mirrors are inclined at an angle theta. So we have two plane mirrors which is inclined or which are inclined at an angle theta. A ray of light is incident on one mirror at an angle I. The ray is reflected from this mirror, falls on the second mirror, and from where it is again reflected back parallel to the first mirror. Then what is the value of the angle of incidence, right? So if this angle is theta, definitely this angle is theta, right? Okay, if this angle is alpha, this angle is alpha. Okay, so beta, from here you can see beta will be equal to theta. Why? Because beta is 90 minus alpha and theta is also 90 minus alpha, because this is the normal. Okay, so from this we will say that beta is equal to theta. So this angle we have already got. Now if this angle is I, if this angle is I, this angle is also I, because angle of incidence is equal to angle of reflection. And if this angle is I, this angle is 90 minus I. Now from this triangle we can clearly see that theta plus beta plus 90 minus I is equal to 180. So from this, what they have asked you, what is the value of I? So value of I will be theta plus beta, that is 2 theta minus 9. So this is the value of I for which the ray finally will emerge parallel to the first mirror. Okay, now we will start with spherical mirrors, right? Spherical mirrors. So suppose this is a sphere and this is a part of a sphere, and this part of the sphere you have silvered. That means you have made it or converted it into a mirror. Okay, so this was a transparent sphere and one portion of it you have silvered, then this portion is a spherical mirror, right? Now this is a three-dimensional figure. You know that the cross section of a sphere will be a circle. So this is a circle. The diameter of this circle, is called the aperture of the mirror. Okay, or you can say it is the aperture diameter. All right. If you want to draw it in two dimensions, then you will draw it like this. Okay. Now there are two types of mirrors or spherical mirrors. One, when you silver it from the outside, that means the inner side is the reflecting side. If the inner side is the reflecting side, in that case that mirror is a concave mirror. Okay, similarly if you silver the inner side, that means the outer side is the reflecting side. If the outer side is the reflecting side, in that case it forms a convex mirror. Okay, so spherical mirror is formed by polishing one surface of a part of a sphere. Depending upon which part is shining, the spherical mirror is classified as concave mirror. So concave mirror, the inner side is shining, and convex mirror, the outer side is shining. Now suppose they have given you the thickness of the mirror. Okay, so they have given you the thickness of the mirror and they have given you the aperture diameter and they have given you the radius. So what is the relation between the radius, the thickness of the mirror and the aperture diameter? Okay, so suppose this is the thickness T and this whole distance is R, right? Because this is the center of curvature, so this distance has to be R. If this is T, this is R, this has to be R minus T, right? This has to be R minus T. Now if the diameter is D, then this radius is D by 2, right? Now you can see that this distance is also R, because distance from the center to the circumference is obviously R. So you can see here that a right angle triangle is getting formed, right? So if the right angle triangle is getting formed, then in this right angle triangle you can say R square is equal to D by 2 whole square plus R minus T whole square. So using this you can get the relation between the radius, the aperture diameter and the thickness. This concept will be mostly useful in questions involving lengths that we will discuss later on, right? Now some more important terminologies. The first thing is the center of curvature. Obviously from this diagram you can see that the center of the sphere of which this mirror is a part, the center of the sphere of which this mirror is a part is called the center of curvature. Okay, so it is represented as C. All right. Then there is a pole. The center of the mirror is called pole. So the center of the mirror is called pole, right? It is represented by P on the mirror. Then the line joining the center of curvature and the pole is called the principal axis. Okay, I'll represent in short form as PA. So the principal axis is a line which is perpendicular to the plane of the mirror. So this line is perpendicular to the plane of the mirror and passes through the pole, right? The principal axis can also be defined as the line which joins the pole to the center of curvature. Okay, and it is also a normal. Why? Because radius is always normal to the sphere surface. Okay, then the next definition is aperture that we have already discussed. Now, one more important definition in this chapter will be what is called as paraxial rays. Okay, what is paraxial rays? Rays which are parallel to the principal axis and which are very close to the principal axis are called paraxial rays. Okay, rays which are parallel to the principal axis and very close to the principal axis are called paraxial rays. So what happens is, in case of paraxial rays, you can say that, see, this is the normal from the center of curvature and this angle I is nearly equal to 0. So the angle of incidence is nearly equal to 0 for paraxial rays. Angle of incidence is nearly equal to 0 for paraxial rays, is nearly equal to 0 for paraxial rays. We will mostly restrict ourselves to paraxial rays for spherical mirrors. Okay, we will restrict ourselves to paraxial rays only in this chapter. Okay, so let us first do this question. I'll tell you why we only use paraxial rays in this chapter, but first let us do one problem. See, in this question it is given that there is a ray of light which is parallel to the principal axis, okay, and after reflection it passes through the pole. It is given that this line is parallel to the principal axis. Then find the angle of incidence theta, right? You know that the normal will be drawn through the center of curvature because radius is always normal to the sphere surface, right? So if this angle is theta, this angle is theta. Why? Because this is the reflected ray. Angle of incidence has to be equal to the angle of reflection because this is normal, right? Okay. Now, if this angle is theta, clearly this angle is theta. Why? Because these two are alternate angles. It is given in the question that these two lines are parallel. Okay. Also, this is radius. This is also radius. That means this triangle is an isosceles triangle, right? So if these two sides are equal, that means if this is theta, this is also theta, but this was also theta, that means this is an equilateral triangle and 3 theta is equal to 180 degree. That means theta is equal to 60 degree. Okay. Now, one more question. Suppose you have a concave mirror here and this is the principal axis. Again, the ray of light is parallel to the principal axis. So this ray of light here is parallel to the principal axis. Okay, and it is reflecting from this surface and it is reaching or striking the principal axis at point F, right? Then we need to find this distance PF, where P is the pole of the mirror. All right, again, this angle is theta, then this angle is also theta. This is the normal from the center of curvature, right? So if this angle is theta, this angle is also theta. Okay, now again what we will see here, if this angle is theta, this is also theta. Why? Because these two rays are parallel and this is a transversal. So if this is theta, this is also theta. Okay, so now this angle is theta, this angle is theta. That means this is an isosceles triangle here, right? Now if this is an isosceles triangle, then the perpendicular drawn from this point F here will be a perpendicular bisector. Okay, now this distance is r. Why? Because the distance from the center of curvature to the circumference is radius, right? So this is r. Now because this is a perpendicular bisector, then this is r by 2, right? So if this is r by 2 and this angle is theta, then this will be how much? This will be r by 2 sec theta. because this is a right angle triangle, right? If this is a right angle triangle, if this is r by 2, then hypotenuse will be r by 2 sec theta, because our hypotenuse is obviously greater than the base, right? Now CP is what? R. Why? Because the line joining the center and the circumference will be equal to R. Okay, the distance between the center and the circumference will be equal to R. So if this is R, then what will be the value of PF? PF will be R minus R by 2 sec theta. Okay, this was what was asked in the question, the value of PF, right? But if the rays are paraxial, what if the rays are paraxial? See, if the rays are paraxial, in that case theta is nearly equal to 0 degree. If theta is nearly equal to 0 degree, then sec 0 is 1. R minus R by 2 becomes R by 2. That is, for paraxial rays, we can say that PF is nearly constant, and that is equal to R by 2. And this focus, this point F is nothing but the principal focus. So again, I'll repeat now. For paraxial rays, I'll define principal focus first. For paraxial rays, this is very important, we have underlined it. For paraxial rays only, light parallel to principal axis, after reflection, passes through a point on the principal axis, or it might appear to pass through a point on the principal axis. So for a concave mirror, it actually passes through the point, this point on the principal axis. But let's see what happens in a convex mirror. In a convex mirror, the center is on the other side. Okay. So this is the normal that we have from the center of curvature. And this will be the reflected rays, right? Okay, you can see that this line and this line cannot intersect this side. It is intersecting virtually behind. So that is why you will say that light which is parallel to the principal axis, after reflection, passes through or appears to pass through a point on the principal axis. This is the point on the principal axis. This is the point on the principal axis. This point is called focus, and the distance between pole and focus is called the focal length, and the focal length for paraxial rays is r by 2. So in this chapter we will deal only with paraxial rays, because only for paraxial rays you can say that the value of focus is constant, otherwise focus will keep on changing. In fact, in the last question what we did was, this was a ray, right, which was parallel to the principal axis, but after reflection it passed through the pole because it was not a paraxial ray. So if the ray is not paraxial, that is if theta is not equal to 0 degree, in that case in that case for different rays, light will pass through different points. Okay, so there will be no fixed value of focus. But if the rays are paraxial, in that case you will say that focus is nearly equal to constant, and that is equal to r by 2, right? So there is a term called spherical aberration. Now what is spherical aberration? Spherical aberration is the defect in image due to the spherical nature of the mirror. Now what is what does this mean? See, you know that focus for paraxial rays is r by 2, but obviously theta is not exactly 0 even for paraxial rays, right? If theta is not exactly 0, then focus is not exactly constant. So for different rays, even if they are paraxial rays, the focus will be slightly different. If the focus is slightly different, that is focus is not a single point, then the image formed is blurred, and this blurriness is called aberration, and this is arising because of the spherical nature of the mirror, so it is called spherical aberration. Now to remove spherical aberration, you can use parabolic mirrors. Parabolic mirrors have such a shape that if a ray is parallel to the principal axis, then after reflection from a parabolic mirror, it will always pass through, or it will exactly pass through the focus of the parabola, all the paraxial rays, means all the rays, even if it is not paraxial, it has to be just parallel to the principal axis, that's it. All the rays which are parallel to the principal axis after reflection is passing exactly through the focus. Okay, so to remove spherical aberration, you can use parabolic mirrors. Then, rules for image formation. What are the rules that we have to use to, form an image? Okay, first point, a ray which is parallel to the principal axis after reflection passes through or appears to pass through focus. This is very, very important. A ray which is parallel to principal axis after reflection passes through or appears to pass through focus. Alright. So if you draw the ray diagram here, we have already drawn the ray diagram. This is nothing but the definition of focus. A ray which is parallel to the principal axis after reflection is passing through the focus. For a concave mirror, there is real focus, and for a convex mirror there is virtual focus. So from here you will say it appears to pass through focus. Okay, so this is a virtual focus here. This is a virtual focus. Then the next point is a ray passing through, or appearing to pass through focus. A ray passing through or appearing to pass through focus emerge parallel to the principal axis. This is nothing but the principle of reversibility of light. See, this is just the reverse case of this. If the ray arrow is reversed, this is reversed. That means a ray which is passing through the focus after reflection becomes parallel to the principal axis. Okay, so in concave mirror it will actually pass through the focus, but in convex mirror the focus is behind. So light ray cannot exactly pass through the focus, means light ray cannot actually pass through the focus. So it will appear to pass through the focus. So when light ray appears to pass through the focus, then it is reflected and it becomes parallel to the principal axis. So this is the second rule for ray tracing. So you can also say this is rules for ray tracing. Rules for ray tracing, right? Then the next point is, this is very important, listen carefully, a ray passing through or appearing to pass through center of curvature retraces its path. This is a very simple point. You know that the radius is always perpendicular to the mirror surface, or spherical surface, right? So, and you also know that if the light is incident perpendicularly to a mirror, it retraces its path, right? So here, if the light is striking perpendicularly, when will it strike perpendicularly? When it passes through the center of curvature. So when light passes through the center of curvature, it will retrace its path. Similarly here also, if light appears to pass through the center of curvature, it will retrace its path. This is the convex mirror and this is a concave mirror. Now one more important point here can be, see, you know that object will always lie on the incident ray, because incident ray originates from the object only, right? So object always lie on the incident ray. Similarly, image will always lie on the reflected ray, because image is what? Point of intersection of the reflected ray. So image will lie on the reflected ray. Object will lie on the incident ray. But look at this line carefully. This line is the incident ray. This line is also the reflected ray. So object will lie on this line only. Image will lie somewhere in this line only. And the center of curvature is also in this line only. That means a very, very important point has emerged here. That is, the object, image and center of curvature are always collinear in a spherical mirror. Object, image and the center of curvature are always collinear in a spherical mirror, right? Then the next point is, you know that this principal axis is a normal, right? Principal axis is a normal because it passes through center of curvature and it is the radius, right? Now, because this is the normal, so a ray which strikes the pole, right, a ray which strikes the pole, right, at particular angle theta, it reflects back at the same angle theta opposite to the principal axis. Okay, so the incident ray was on one side of the principal axis, the reflected ray will be at the same angle but on the other side of the principal axis. So when light will be incident on the pole, there will be a symmetric reflected ray with respect to the principal axis. This is true not only for the concave mirror but also for the convex mirror, because for convex mirror also this is the perpendicular, right? Okay, but there is one more important point here. Suppose the object is in this line, because this is the incident ray, so the object is in somewhere in this line. Suppose this is the object and the image is somewhere in this line. Suppose this is the image, right? Then this is the image and this point I dash is called the conjugate of the image. This is the symmetric point of the image on the incident ray. All right, so this is the conjugate point. The object, the conjugate point of image and the pole are always collinear. Similarly, if this is the object, this is O dash. O dash is the conjugate point of the object on the reflected ray. Conjugate point of the object, the image and the pole are always collinear. Now, we have seen here there are 4 rules for ray tracing. You know that for forming an image you need only 2 rays, right? So out of these 4 rules, you can use any 2 rules to find the image. Okay, now we will discuss sign convention. Now this is very important, because if you do not put proper sign, then you will not get the correct result in the mirror formula. So you have to understand how to write proper sign. Okay, see, first is for measurements along the axis. So if you want to measure anything which is along the axis, right, in that case, first thing is all distances are measured from the pole. All distances are measured from the pole. Okay, first. Second thing, all distances which are in the front of, or which are measured in the front of the optical instrument, are negative. So suppose this is the object here and starting from the pole, this distance is negative. Why? Because it is in front of the optical instrument. If it is behind the optical instrument, then that distance will be positive. So again I'll repeat, all distance in front of an optical instrument is negative and all distances which are behind the optical instrument is positive. So this is a general sign convention which will be used not only in spherical mirrors but also in lens and also in refraction. Okay, so first thing, again I'll repeat here, all distances in front, or all distance measured in front of the optical instrument is negative. Now what is the meaning of front? Front means where incident rays lies. Okay, front means what? Front does not mean the left side or the right side. Front means where incident ray lies. Front means where incident ray lies. That's it. There is one more way of explaining this same point. That is, you know that you have to start from you have to start from pole to measure the distance, right? You have to start from pole to measure the distance. So if starting from pole, if we are moving along the incident ray, then that distance will be positive. And if we are moving opposite to the incident ray, then that distance will be negative. So here, if we are moving opposite to the incident ray, see, we have to start from pole and the incident ray is moving like this. So to measure this distance starting from pole, we have to move opposite to incident ray. If you move opposite to incident ray, then that distance is negative. So the second and third points are basically the same thing, but they are explained in a different manner. That's it. So the easiest way to remember is the second point. All distances which are in front of the optical instrument is negative and all distances behind the optical instrument is positive. Okay, and what is front? Front means the region where the incident ray lies. All right. So now case 2, when you want to measure something which is perpendicular to the principal axis, then this is very simple. Above the principal axis, all distances will be positive and below the principal axis, all distances will be negative. Now Object distance. Object distance means the distance of the object from the pole is represented by u, and image distance is represented by v. Okay, then what is the sign convention? Listen carefully now. Real object, you know that real object is always in front, right? Real object is always in front and rays divert from real object, right? So if the object is in front and this is the distance, then you will say that the real object distance is negative. So real object distance u is negative. You have to remember this sign convention. For real object, u is always negative. So if it is given to you that object is at a distance of 25 centimeter in front of a mirror, that means the object distance is minus 25 centimeter. Okay, all distances measured in front of the optical instrument is negative. So u is negative for real object. If you have a virtual object, you know that virtual object is behind an optical instrument. Now all distances measured behind an optical instrument are positive. So here you will say that u is positive. Okay, u is positive. Then comes image. Now real image, and then there is virtual image. Okay, now first is for real image. Listen carefully, because there can be reflection as well as refraction. So first I will write for reflection and then for refraction. Okay, now you know that in case of reflection, light comes back to the same medium. So image means what? Intersection of reflected rays. Now if there is actual intersection, only then real image can be formed, right? So here if there is actual intersection, then only real image can be formed. Okay, and actual intersection can only be in front, right? Behind there is no actual ray. So actual intersection can only be on the front side in case of reflection. So front distances are negative, right? So real image reflection, real image distance is negative. But for refraction, you know that light moves to the other side. Now if light moves to the other side, what does this mean? This means that the real image in case of refraction will be positive. Why? Because it is behind the optical instrument. All distances behind the optical instrument are positive. Okay, so that means we will say that for refraction the real image distance is positive. Similarly for virtual image, what we will do for virtual image, again the same thing. For reflection it will be behind, that is positive, and for refraction it will be in front. For refraction it will be in front and that will be negative. Okay, then comes focus or the radius of curvature. Focus or the radius of curvature, sign convention of focus or the radius of curvature. See, for a concave mirror, we know that the center is in front. That means the radius is in front. Okay, radius is measured in front of the instrument. But for a convex mirror, the radius is measured behind the optical instrument, right? This is convex mirror. So front distances are negative. So focus and radius of concave mirror is negative and convex mirror is positive. That means in question, if it is given to you that focus of a concave mirror is 20 centimeter, you will write f is not 20, you will write f is minus 20. Focus of a concave mirror is negative and focus of a convex mirror is positive, right? Okay, then image formed by a concave mirror. So formation of image by a concave mirror. We will do case by case. First is the real object. Okay, so image formation by concave mirror for real objects. Now real objects, there will be 5 cases here. First case is when object is at infinity. When object is at infinity, image is formed at focus or focal plane. We will discuss that in details. The second thing is when the object is between infinity and 2f. 2f means the center of curvature. Why? Because f is equal to r by 2. We have already discussed f is r by 2. So r is equal to 2f. So that means 2f is the center of curvature. So when the object is between infinity and the center of curvature, in that case real image is formed. Inverted image is formed, you have to remember this, and diminished image is formed. Also, the image formed is between f and 2f. You have to remember, when the object is between infinity and 2f, image is real, inverted and diminished, and it is formed between f and 2f. So image is beyond 2f, object is beyond 2f, image is between f and 2f. The next case is when object is at 2f. When object is at 2f, image is also at 2f, and image is real, inverted and same size. You have to remember, I'll draw the ray diagrams of each of this case, but you have to remember it. You learn it. Okay, take a pause and learn it there itself. Okay, so then when the object is between f and 2f, when the object is between f and 2f, in that case image is formed beyond 2f and the image is real, inverted and magnified. Okay, then the next case is when the object is at focus. When the object is at focus, image is at infinity. In this case, the image is real, inverted and highly enlarged. It's so extremely enlarged that you cannot even see it, that image, right? Then the next is when the object is between pole and focus. Now in this case, the image is formed anywhere between pole and infinity, but behind. Image is formed between pole and infinity behind. Image is formed between pole and infinity behind. That means what? That means the image is virtual. Okay, you have to remember, the image is virtual, erect and magnified. Image is virtual, erect and magnified. Image is virtual, erect and magnified. Okay, now from this, what you can see? We can see that concave mirror is forming virtual image only in one case. In which case? When the object is between pole and focus. But you can see that this virtual image is not means it's not diminished, it is magnified. That means if a concave mirror is forming a virtual image, it has to be magnified. In other words, you can say that a concave mirror cannot form diminished virtual image. So here I have written it here. Concave mirror can form virtual image when object is between pole and focus, and this image is magnified. So when object is between pole and focus, it is forming a virtual image, but this image is magnified. A concave mirror cannot form diminished virtual image. So if it is given to you that a mirror is forming a virtual image and it is magnified, then you will know that that mirror is a concave mirror. Okay, then the next case is virtual object. So virtual object means object is behind the optical instrument. When object is behind the optical instrument, in that case there is only one case. When object is anywhere between pole and infinity, anywhere, image is always formed between pole and focus in front. Image is always formed in between pole and focus in front. That means it is real. Okay, image is real, erect and diminished. Image is real, erect and diminished. That means for virtual object, concave mirror cannot form virtual image. Concave mirror also cannot form magnified image for virtual object. For virtual object, image will always be real and diminished and erect. Okay, now there is one important thing that will help you memorize these. That is, if you have a real object, and from that real object a real image is formed, then that real image is always inverted. Again, I'll repeat. If you have a real object and from that real object, using any optical instrument, a real image is formed, then that real image is inverted. Similarly, you have a real object, but from that real object, using any optical instrument, a virtual image is formed, then that virtual image is always erect. So for real object, real image is always inverted and virtual image is always erect. If you have a virtual object, then the things reverse. If you have a virtual object and a real image is formed, for example this case, here there is a virtual object, and for virtual object always a real image is formed in case of a concave mirror, right? But this time the real image is not inverted but erect. This time the real image is erect. Similarly, if a virtual object gives you a virtual image, concave mirror will not give you a virtual image for virtual object, but convex mirror will give you a virtual image for virtual object. That we will discuss now. Okay. So if virtual object forms a real image, it is erect. But if virtual object forms a virtual image, it is inverted. So there is a difference here. Again, I'll repeat, for real object, if there is a real image, it is inverted. And if it is a virtual image, it is erect. But for virtual object, if it is a real image, it is erect. And for virtual image, if it is inverted. All right. Now, when object is at infinity, object is at infinity, that means there is a parallel beam of light which is okay. So when object is at infinity, we know that the image is formed at focus or the focal, right? So let us draw the ray diagram. So this is the means parallel beam of light. So the rays are coming from infinity, and after reflection, obviously a parallel beam of light will pass through focus. Okay, but the parallel beam of light is not necessarily parallel to the principal axis. It's like this also, right? It can come like that from a distant object. So if the rays are coming like this, then you have to draw two rays. So let the first ray be a ray passing through center of curvature retraces its path, right? So this is the first ray. And the second ray is, you know that a ray which is passing through pole comes at the same angle from the pole, okay, on the other side. So this angle is theta, this angle is also theta, right? Now this is the reflected ray and this is also the reflected ray. The intersection of these two reflected ray will give you the image. This image is formed in the focal plane. What is the focal plane? A plane which contains the focus and is principal and is perpendicular to the principal axis is called the focal plane, right? Suppose this angle is theta, that means the rays are coming or the rays are striking the principal axis at an angle theta, and this angle is also theta. Why? Because angle of incidence will be equal to the angle of reflection. Then you will say that tan theta is equal to, suppose the height of image is h, then tan theta is nearly equal to theta is equal to h by f. Okay, tan theta is nearly equal to theta is equal to h by f, or you can say that height of image is equal to theta f. Now the next case is when the object is between infinity and center of curvature. So this is the center of curvature and this is infinity, and the object is between center of curvature and infinity. We know that the image is formed between the focus and the center of curvature, or you can say between f and 2f, right? So let us draw the ray diagram. We have seen that there are 4 rules for ray tracing. Out of that 4 rules, we will draw any 2 rays. We can draw any 2 rules, okay? So let us say we know that a ray passing through center of curvature retraces its path. So this is the third rule. And we also know that a ray passing through focus after reflection emerge parallel to the principal axis. This is the second rule. Okay, so we have used the second and the third rule. Now this is a reflected ray, this is a reflected ray. The point of intersection of reflected ray, this one is the image, right? So this point image is here and this point image will be here. So the object is this, image is this. You can see that the image is diminished. So what will you say finally? The image is between f and 2f, right? So it is between the focus and the center of curvature, and the image is real because there is actual intersection. It is inverted because the object was above the principal axis and the image is below the principal axis, and diminished. Small means diminished. Okay. Then the next case is when the object is at 2f. When the object is at 2f, okay. So let us use the first rule in this ray diagram. The first rule is a ray parallel to principal axis after reflection passes through focus. Let us also use the second rule. What is the second rule? A ray which is passing through the focus after reflection becomes parallel to the principal axis. Now this is a reflected ray, this is a reflected ray. The intersection of two reflected rays will give you the center of, the image, right? And you can see here the image is formed at the center of curvature only. So when object is at 2f, image is at 2f, or you can say image is at the center of curvature. This image is real, inverted and same size. Okay, same size means size of image is same as size of object. All right. Then the next case is when the object is between f and 2f. When the object is between f and 2f, right? So again, let us use the first rule. The first rule is what? A ray parallel to principal axis after reflection passes through focus. And suppose we use the fourth rule, that is a ray which is symmetrically incident at the pole, okay, emerge symmetrically on the opposite side. Okay, that means at the same angle, right? So this is the reflected ray, this is the reflected ray, the point of intersection is this, then this is the image. You can see that there is actual intersection, that means this image is real. So you will say that this time the image is formed beyond the center of curvature. Okay, so that is image is formed between center of curvature and infinity, right? Image is real, inverted and enlarged. You can see that this time the image is enlarged. Okay, then when the object is at focus, when the object is at focus, in that case let us use the first rule, that is a ray parallel to principal axis after reflection passes through focus. This is the first rule. The second rule is a ray which is passing through the center of curvature. So a ray which is passing through the center of curvature, right? A ray which is passing through the center of curvature after reflection retraces its path, right? So this is the one ray and this is one more ray. Both these rays are parallel, that means they will never intersect. They will intersect at infinity, right? So image is formed at infinity. So in this case the image is formed at infinity, right? And image is real, inverted and extremely large. It is so large that you cannot see it, right? Then the next case is when the object is between pole and focus. When the object is between pole and focus, again let us use the first rule. When a ray is parallel to the principal axis, then after reflection it passes through the principal focus. And let us use the fourth rule, a ray which is symmetrically incident on the principal axis on the pole, okay, then emerge symmetrically with respect to the principal axis, right? So this is the reflected ray, this is the reflected ray. Now here it is not intersecting, it is intersecting behind the mirror. That means the intersection is virtual, that means the image is virtual. Okay, the image is virtual, it is erect and enlarged. I've already told you, for real object real image is always inverted and virtual image is always erect, right? And this virtual image here is enlarged. That means a concave mirror can form virtual image in only one case, that is when the object is between pole and focus and this image is enlarged. A concave mirror cannot form diminished virtual image for real objects, right? And for virtual object there is only one case in a concave mirror, that is when object is anywhere between pole and infinity behind. Behind means virtual. Okay, so when object is anywhere between pole and infinity behind, image is always real, erect and diminished, right? For virtual object real image is always erect, okay, and image is diminished. That means for virtual object a concave mirror cannot magnify a virtual object, okay, it can only decrease the size, not increase the size, right? Then image formation by convex mirror. Okay, image formation by convex mirror. Case 1, real object. So first let us see what happens for a real object. For a convex mirror in real object there is only two cases. First case is when the object is at infinity, image is at focus. Okay, this image is virtual and erect and it is very small. Or you can also say image is formed at the focal plane. Let us draw the ray diagram when the image is formed at the focal plane, because it is not necessary that a parallel beam of light which is coming is parallel to the principal axis. Okay, from infinity rays, parallel rays can come and it is not necessarily parallel to the principal axis. So if the rays are not parallel to the principal axis, in that case what will you say? See, in that case let us draw the ray diagram. Let us use the fourth point, this one, symmetric point, right? And also let us use the third point, or you can say we can use the second point, a ray which is parallel to the principal axis, or you can say a ray which is appearing to pass through the focus after reflection emerge parallel to the principal. Okay, so here this is the reflected ray, this is the reflected ray, and the point of intersection will be behind at this point, and this is nothing but the focus, and the image is formed at the focal plane. Image is formed at the focal plane. Image is formed at the focal plane. Okay, then there is only two cases here. The second case is when object is anywhere between pole and infinity. So when object is anywhere between pole and infinity, in that case image is always formed between pole and focus. Now what does this mean? Let us see. So I'll draw it here. Suppose you have a object which is anywhere between pole and infinity, anywhere. Okay, and let us use the first point, that is a ray which is parallel to the principal axis after reflection appears to pass through the focus. Okay, this is the first relation. Then the second ray diagram that we will draw here is the fourth rule, that is the symmetric rule. A ray which is incident on the pole, okay, is reflected symmetrically on the other side of the principal axis, right? So this is the point of intersection. You can clearly see from here that the image is formed between pole and focus. Image is always formed between pole and focus. Image is behind the mirror, that means it is virtual and it is erect, right? So, and also it is diminished. So what will you say? You will say that a convex mirror for real object can never form a real image. It always forms a virtual image, right? And that virtual image is always erect and diminished. Okay, but what happens in case of a virtual object? So in case of virtual object, there are, you will see that in case of virtual object there are four cases. First, when the object is between 2f and infinity. When the object is between 2f and infinity, then the image is between f and 2f. So when the object is beyond 2f, the image is between f and 2f, and the image is virtual, inverted and diminished. Listen carefully. The results are similar to what you got for real object in a concave mirror. Real object in a concave mirror will give you similar result as virtual object in a convex mirror. But there will be only one difference. And what will be that difference? That difference is wherever there was real image in case of concave mirror, real object, here there will be virtual image for virtual object in convex mirror. Okay, so if you remember, when the object was beyond 2f in concave mirror, the image was between f and 2f. Image was real, inverted, diminished. Here everything is same. When object is beyond 2f, image is between f and 2f. The only difference is the image is not real but virtual. So image is virtual, inverted and diminished, right? Then the second case is when the object is at 2f, the image is at 2f. Again the image is virtual, inverted, same size. The only difference that will come is real will become virtual and virtual will become real. That's it. Okay. Then when the object is between f and 2f, the image is beyond 2f. Image is virtual, inverted, magnified. Everything is same, only this change. R becomes V. Okay. Then when the object is between pole and focus, when the object is between pole and focus, then image is formed anywhere between pole and infinity. Image is formed anywhere between pole and infinity in front. In front. That means what? Image is real. So this time the image will be real. So object between pole and focus, image will be anywhere between pole and infinity, and the image will be real, inverted and magnified. Okay. So that means a convex mirror cannot form real image for real object, but it can form real image for virtual object in one case. And which case is that? That case is when the object is between pole and focus. When the object is between pole and focus, in that case the image is real, okay, for virtual objects in convex mirror, right? So, and this real image is always magnified. That means a convex mirror cannot form a diminished real image. Okay, a convex mirror can form real image only in one case, that is when object is virtual and it is between pole and focus, and this image is always magnified. A convex mirror cannot form a diminished real image under any circumstance. Okay, so with this we come to the end of today's class. Tomorrow or in the next class, what we will do is we will start with mirror formula and applications of mirror formula. We'll also derive the mirror formula in the next class. Till then, stay tuned, and if you like my video, please like, share and subscribe to my channel. Okay, bye bye then. See you in the next class.